Hey, good morning, everyone. Thanks again for a nice alternative audience again today. I'll be very brief. I'm going to introduce Miguel Bustamante. He's going to talk about fluid dynamics today, so slightly different. He's an applied associate professor and applied mathematician and physicist in the School of Maths and Statistics. So at that, I'll hand over and I'll talk again about a few events that we've coming up, but hand it over to Florian.
Many thanks. So thanks to the Earth Institute and all the staff for their kind invitation. Okay, so just quickly, my CV somehow in a page, but just wanted to tell you I've been here since 2009, so I've seen several changes. I've occupied 4 different offices because they've been moving us up and down. And I'm here in the, proud to be in the Earth Institute since 2023, but, I was collaborating with people from the Institute for years before. And another thing that I want to mention is, and I will mention at the end, is that I'm organizing, along with a couple of colleagues from UCD, the largest European Fluid Dynamics Conference. It is under the aegis of EuroMech, the society, the European Mechanics Society. So it's the real deal. And we're going to expect a lot of over 1,000 delegates, and it's going to happen in the next year, in August, the last week of August. Okay, so let us start from this nice painting. I don't know if have you been to Louvre? Yeah, so I've seen the Gioconda and so on. But there are many other nice paintings from Leonardo. I actually prefer the one that is outside that corridor where Gioconda is. And of course, this one is just a drawing he did. This is not in the Louvre, but it's still very nice. So what do you see here? It is so-called studies of water. So from the top right corner, there is a gate, and water is coming out of that gate on some pool, all right, of water. And you can see these curly trajectories. So you can see these large, long ones, right, corresponding to large scale motion. But then you can see, each time you look at it more closely, you see a smaller and smaller curl is forming. There's also a 3-dimensional component to it, like below the surface of the water, because there's also flow in that direction. And on the surface, you can see even smaller and smaller vortices and kind of bubbles and stuff like that. So he was basically understanding, notice the year, right? So this is before Galileo, before science, right? This guy was really ahead of his time, trying to understand what was happening in nature. And nowadays, this picture, it's competes very well with what people are trying to understand from point of view of engineering, from point of view of pure mathematics. Like all the convergence of the different areas of science are still trying to understand this phenomenon. Why? Because it's so complicated, right? It's full of things going up and down, some chaotic, right? We can think of the concept of chaos, and still we're far from understanding it. In particular, okay, here it's a bit, I think, yeah, from this angle, it's hard to see, but I think the ones who are in front of the TV, they can see what's happening here, right? Another drawing from Leonardo, he drew himself there looking at the thing. Like, I mean, he was a genius. Like he would spend, a couple of minutes to draw beautiful pictures. So he drew himself there looking, thinking. And what is he thinking of? It's observing the flow. Again, say, suppose you have a river and you have some poles and the water is flowing past those poles. And what happens is behind those poles, the water starts curling around and forming these nice patterns. And he called this turbulenza. I'm not Italian. I don't even speak Italian. So, but it is, they say, I mean, there's a little bit of controversy there who, what he meant by turbulenza. Some people say maybe he meant turbidity of water and not this state of motion. But anyway, he obviously was aware that there was something nice going on there, and that later, it would start very strong and then decay kind of far away from the obstacle. All right. So yeah, so with that, we can start moving on to the future. Say still 400 years later, nothing has happened too much, from that original observation of Leonardo. People are doing experiments trying to understand, of course, and there's been a lot of definitions of what turbulence is, right? So, for example, in this experiment, you have flow going through a pipe, and by Reynolds, and he puts some dye in this flow, and depending on the speed of the flow, you can find different behavior. For example, for small speeds, the dye just remains nicely confined to the middle, but then for larger speeds, you can start some instability, right? So some perturbation in the flow that is natural, because remember, there are 10 to 23 molecules and so on per cubic centimeter. So there's going to be a little bit of noise, and this noise will intensify, they will amplify. But turbulence is very interesting in that it is kind of self-organizing. It is complex and chaotic, but in the end, it forms some structures. And that's the part where mathematics can try to say something about it by modeling this problem with simple concepts that kind of put together all this chaos into one coherent structure. For example, the flow past a wall. I mean, maybe you've seen pictures or videos of airplanes and I mean, maybe you've seen these jets that look like coming from the airplanes, but it's actually some instability that forms. And when you look at the motion of the flow near the wall, it looks like this so-called hairpin vortices. It is kind of rolls of the air that, because it's passing along a wall, it starts rolling around, but it is stuck to the surface somehow. So you get this kind of nice patterns. So yeah, two examples of what people have tried to do in terms of modeling the phenomena that is turbulence. So it's very complex. So I'm going to talk about two examples that I've been involved with over the past years. And as I said, well, as I was reading there, this is a problem that involves interdisciplinary work always. So there's always some mathematicians, pure mathematicians, maybe even working on some very difficult problems. And then you have the engineers, and then you cannot talk to each other because it's they're too far away. So you need people in between. And that's what's happening, right? So we're creating more and more disciplines in between to basically be able to converse and go all the way from one to the other. Okay, so here's an example of a nice problem that involves all these nice conversations. So again, you can think of it as the problem that Leonardo was studying, is the flow past a cylinder. So, so you have a cylinder there, kind of horizontally placed, and you have flow, say, from behind the screen, right, going towards us. And this flow will pass around the cylinder. And if the speed is not too large, so the slow flow, the motion is going to be so-called laminar, and the trajectories are going to be very nice and easy to understand. I mean, there will be some deformation, but they will be nice and easy. If you increase the speed of flow, you start getting interesting behavior, interesting structures forming. Usually on the other face, not on the face of the cylinder that receives the flow, but on the face behind it, right? And when the speed is very large, you end up with this kind of nice pattern behavior, right? And when you look at it, it's flow that is impinging there on the along the cylinder surface, but then because the water could be water or air, assuming incompressibility, which is a good approximation, the flow that is trying to collide, right, coming from the upper part and from the lower part, will eventually continue in the direction out of the plane. But in so doing, it's going to start also forming vorticity, or this rotation, these helical patterns, right? So to do these simulations on a computer takes days, right? And a lot of resources. So, when you're calculating, for example, the pressure, which is one of the things that people want to know, because from engineering's perspective, you want to know if you have a real life pole, right? And you want to calculate, will it break or not? So you need to calculate these quantities such as pressure. Then you do need this large computational power. However, to understand this phenomenon, you can just do a nice model. In this case, is a plane where you simply forget about all this curvature of the cylinder and just consider a flow in a plane. So this is the only slide with equations, right? Just to show you the inner workings of me, with the formulas and so on. But basically, what it is saying is we're solving the basic equations, the Euler fluid equations, and there's two quantities involved. One of them tells you how much the flow is coming, colliding along the plane, and the other one is telling you how much it is rotating with respect to itself. That's all. Those two quantities tell you everything. And this model, you can solve everything analytically with pen and paper. So when we plug the solution, so basically the story here, this is the plane, flow is coming from the top vertically downwards, and here from the bottom is vertically upwards. And that's the situation. And then you run this model as a function of time. I don't know if you can see what's happening there with the, do you see any pattern forming there? Yeah. So yeah, because it's happening that the flow doesn't want to go precisely like that. It will slightly deform by a small perturbation, and then we'll start doing this game of the three-dimensional helical motion. In this plot, of course, you don't see the three-dimensional motion, but believe me, you can calculate it from the model. It's not difficult. Again, everything can be calculated analytically in this case. So which is great, because then you can compare that model with real life, with high computational power, and basically all the characteristics are appropriately modeled, correctly predicted, right? All these patterns, all these pressure points can be predicted. So it's very powerful to have something that you can compare with pen and paper rather than just believing, that hoping that your computational method is good. Okay, so that's that system. Here is a real life problem that my colleague Hoffman, who I'm collaborating with, did a few years ago. they were basically calculating the noise that is made by the landing gear. And for that, it's due to this flow, right? So here is an actual experiment, and you can see I'm not sure if you can see it, but it's full of little lines around and corresponding to the trajectories of the particles. And this is the theoretical prediction of that. So they look very similar. I mean, of course, you're not going to get exact matching, but at least, and you can see here, these vortices that were forming there. So like all the basic characteristics are there in the little model that you can do. So, okay, maybe 2 more minutes and I'm gone. Yeah. Thank you for that. So second point I wanted to discuss, and here Connor, maybe he's very knowledgeable, of course, as you know, about what's happening in the atmosphere, but still I'm going to take the risk and talk about it. The scenario I want to discuss is a scenario where you have competition between two time scales. So in nature, for example, in this case, the Earth rotation is once a day, right? And it produces atmospheric waves with a similar time scale, very close to days, could be hours or so. And these waves actually exist in the atmosphere. This is kind of a depiction of them, right? And they correspond to masses of air that move. They're oscillatory in the spatial direction and also in time. But when you look at these Euler equations that I was showing you, which are nonlinear equations, they contain on their own extra time scales that depend on the amplitude of the oscillations. So for very large amplitudes, they're very fast, and for small amplitudes, they're very slow. And so it happens that if you pick the right amplitude, you can have a resonance, which is when the two time scales, one from the natural time scales of the waves and the other time scale coming from the nonlinear oscillation, when these two time scales coincide or get close enough, they can start talking to each other, giving energy from one to the other. And that's when things get very interesting, because you start getting phenomenon that can last for years or even millennia, depending on the system. For example, on Earth, it makes sense to talk about 100 years and so on. On the sun, which you can also apply this method for the sun motion. So, the formation of the little sunspots is the right thing there to talk about. Also depends on this interesting relation between time and scale. So again, the little plane there, forget about all the complications, just a little plane, and then model that. In this case, there's no exact analytical solutions, but it's very close, and you can actually follow up conservation of quantities very carefully. So you still have a model that is numerical, but it's based on a very good ground analytically. And you can prove that this phenomenon occurs. So when the amplitudes are low, the waves dominate, and you just have the usual waves and nothing happens. It's kind of boring. I mean, the waves are nice and beautiful. You can see sometimes the waves forming when there's a little bit of clouds. Yeah, but it's not the turbulence that we go. And then on the other side, when the amplitudes are very large, it is this long motion that dominates, and you end up with these large vortices dominating the whole atmosphere, like in Jupiter, the red spot. That would be a good example. It dominates for eons, right? It doesn't dissipate. But when you pick the intermediate amplitude, which actually happens to be close to the amplitudes that actually the Earth is choosing, right, in their dynamics, you get something in the between. There's a competition between the energies of the waves and the energies of the big vortex, and you get what is called turbulence, right? But this is a different type of turbulence, not the one you saw in the first part. Yeah. Okay, so that's the story there. And I want to finish with the invitation to everyone to our second European Fluid Dynamics Conference, which will take place here in UCD in August 2025. Please save the date and look at the beautiful logo we have. It's the largest European Fluid Dynamics Conference. And we're very proud that we nailed that conference to be here in UCD. We expect over 1,000 delegates, and we're going to have everything in terms of fluid dynamics, not just the mathematicians, like aerodynamics, atmospheric flows, industrial applications, wind and water power. So thank you for your attention, and invitation is there.